Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet mystery of Three-Eye Atlas, a visitor from another star system that carries within its ancient ice the chemical memory of a distant stellar birth. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On a September evening in 2019, automated telescopes scanning the southern sky capture something unusual, a faint smudge of light moving against the starfield with peculiar speed. The object designated Three-Eye Atlas appears unremarkable at first glance, another small body tumbling through the solar system's outer reaches. Yet within hours, orbital calculations reveal its true nature. This visitor follows a hyperbolic trajectory, meaning it originated beyond the Sun's gravitational influence and will never return. The mathematics are unforgiving in their precision, eccentricity greater than 1, velocity exceeding escape speed, a cosmic wanderer that has crossed the emptiness between stars. The discovery represents only the third confirmed interstellar object detected in human history. Unlike asteroids born within our solar system's chaotic early formation, Three-Eye Atlas carries materials forged in the nuclear furnace of a different star, cooled in the disk of another planetary system, and aged through millions of years drifting in the vast spaces between stellar neighborhoods. Its arrival offers scientists an unprecedented opportunity to examine matter that condensed under alien conditions, isotopes that whisper foreign stellar chemistry, minerals that crystallized in temperatures and pressures unknown to Earth's formation. The comet's nucleus measures perhaps 2 kilometers across, small enough to hold in a city block, yet massive enough to preserve primordial materials unchanged since its birth. As it approaches the inner solar system, solar radiation begins sublimating its surface ices, creating the characteristic coma, a glowing atmosphere of gas and dust that allows spectroscopic analysis of its composition. Each photon absorbed and re-emitted by these liberated molecules carries information about the stellar environment where they first formed, like archaeological artifact preserved in frozen time. Astronomers worldwide coordinate observations, knowing this celestial immigrant will make its closest approach to the Sun and then continue its journey into interstellar space, never to be seen again by human eyes. The observational window spans mere months, a blink in cosmic terms, yet an eternity in human planning. Telescopes in Chile track its southern passage while Hawaiian instruments capture its northern arc, creating a global network focused on this single dim visitor that carries within its icy heart the chemistry of another world. The comet's surface reflects only 4% of incident sunlight, darker than charcoal, suggesting organic compounds baked and radiation weathered during its interstellar journey. This carbonaceous patina speaks of eons spent exposed to cosmic rays and high-energy particles that strip electrons from atoms and break molecular bonds with relentless patience. Each grain of surface dust bears the scars of impacts from interstellar particles traveling at hundreds of kilometers per second, microscopic collisions that have sandblasted the comet's exterior into a complex regolith of shattered ice and altered minerals. Only took 4.5 billion years to arrange this brief meeting. The universe operates on schedules that make human lifespans seem like flickering moments, yet somehow aligns cosmic mechanics to deliver this messenger from the stars directly into the path of a species curious enough to recognize its significance. The gravitational dance that brought 3i Atlas through the outer reaches of the Oort cloud and into the inner solar system required precise timing, arriving just as humanity developed the technology to detect and analyze such visitors. In observatories across the globe, sensitive instruments train their focus on the approaching visitor, beginning the careful work of decoding its chemical autobiography. Spectrographs split the comet's faint light into constituent wavelengths, revealing absorption lines that correspond to specific molecules sublimating from its nucleus. Each spectral signature represents a different compound water ice, carbon monoxide, methane, ammonia, but the ratios differ subtly from solar system comets, hinting at formation conditions unlike those that shaped our local celestial bodies. The mystery deepens as initial observations reveal isotopic anomalies in the comet's composition. The ratio of heavy to light water molecules deviates from the solar system norm, suggesting condensation in a stellar nebula with different nuclear processing history. Nitrogen isotope ratios similarly diverge from local standards, indicating formation in a region where supernovae or stellar winds had altered the primordial gas composition in ways unknown to our Sun's birth environment. Radio telescopes join the observational campaign, detecting emissions from hydrogen cyanide and other organic molecules as they sublimate into the comet's growing coma. These complex carbon-nitrogen compounds form readily in the cold, radiation-rich environment of interstellar space, where molecules can assemble slowly over millions of years without the disruptive heat of nearby stars. The detection of such compounds raises questions about the universality of organic chemistry, whether the building blocks of life arise through similar pathways around different stars, or whether each stellar system develops its own unique molecular inventory. As 3i Atlas continues its approach toward perihelion, the point of closest solar approach, its activity increases steadily. Jets of sublimating gas and dust create asymmetric features in the coma, indicating discrete active regions on the nuclear surface where subsurface ice encounters solar heating. These outgassing events provide scientists with fresh samples of the comet's interior composition, materials that have remained frozen and unaltered since the object's formation in its distant birth system. The timing of this discovery feels almost serendipitous, arriving just as humanity has developed sophisticated instruments capable of analyzing interstellar chemistry in real time. Previous generations of astronomers could only wonder about the composition of matter beyond the solar system, limited to observing distant stars through crude optical telescopes. Now, this visitor brings samples of alien stellar chemistry directly to Earth's vicinity, close enough for detailed spectroscopic investigation and theoretical modeling. The comet's trajectory suggests it has spent several million years crossing the interstellar medium, travelling perhaps 50 light-years from its origin point to reach our solar system. During this journey, it encountered varying densities of interstellar gas and dust, different radiation environments, and the gravitational influences of multiple stellar systems. Each of these encounters has left subtle traces in its composition and structure, a palimpsest of cosmic wandering written in isotope ratios and mineral textures. The mathematics of 3i Atlas's trajectory tell a story written in gravitational poetry, each orbital element revealing chapters of its cosmic wandering. Astronomers trace the comet's path backward through time, calculating its motion through the galaxy's spiral arms with the precision of celestial archaeologists. The object's current velocity of 26 kilometers per second relative to the Sun suggests it has travelled for approximately 3 million years since escaping its parent star system, drifting through the local bubble, a cavity in the interstellar medium carved by ancient supernovae explosions. Galactic motion models indicate 3I Atlas originated roughly 50 light-years away, possibly from the stellar association known as the Scorpius-Centaurus OB complex, where massive young stars illuminate vast nebular clouds with their fierce radiation. This region harbours dozens of star systems less than 20 million years old stellar nurseries, where planetary formation remains active, and where gravitational interactions between newborn planets can eject cometary bodies into interstellar space. The comet's trajectory aligns with the motion of this stellar group, suggesting it was born in the debris disk of a star that has since evolved beyond its planet-forming phase. The precision required for such calculations astounds even the astronomers performing them. Tracing an object's path through 3 million years of galactic motion requires accounting for the gravitational influence of every significant mass within 100 light-year radius, the combined pull of red giants, white dwarfs, stellar remnants, and the distributed mass of interstellar gas clouds. Each gravitational encounter, however slight, alters the trajectory by minute amounts that accumulate over cosmic timescales into major changes in direction and velocity. Computer models simulate the comet's journey through the galaxy's rotating disk, where stellar densities vary dramatically between spiral arms and the quieter spaces between them. During its wandering, the Atlas likely passed within a few light-years of several star systems, experiencing subtle gravitational tugs that modified its course while preserving its essential interstellar trajectory. These close encounters with foreign suns exposed the comet to varying intensities of stellar wind and radiation, contributing to the weathering patterns now visible on its surface. The local standard of rest, the average motion of stars in the Sun's galactic neighbourhood, provides the reference frame for understanding 3 Atlas's unusual velocity. Most objects in the solar system move with velocities measured in tens of kilometers per second relative to the Sun, but interstellar visitors arrive with velocities that reflect galactic rotation and the peculiar motion of their origin stars. The comet's approach angle and speed encode information about the kinematics of its birth region, allowing astronomers to constrain which stellar associations could have produced such a wanderer. Only took 3 million years of patient drifting to reach our corner of the galaxy. The comet's journey spans a period when early human ancestors were first using stone tools. Yet 3 Atlas experienced this entire evolutionary epoch as a single, uninterrupted fall through the cosmic dark. Timescales that encompass the rise of human civilization represent mere moments in the comet's interstellar odyssey, a reminder that celestial mechanics operate according to rhythms that dwarf biological evolution. Stellar proper motions complicate the backward integration of the comet's trajectory. Each star in the galaxy follows its own orbital path around the galactic center, creating a complex dance of gravitational influences that change over millions of years. Stars that appear close together in the current epoch may have been separated by dozens of light-years when 3I Atlas began its journey, while stars currently distant may have provided significant gravitational perturbations during the comet's early interstellar wandering. The Gaia Space Telescope's precise measurements of stellar positions and velocities prove essential for these calculations. By mapping the 3-dimensional motions of over 1 billion stars, Gaia provides the data necessary to model the galaxy's gravitational environment as it existed millions of years ago. This stellar census allows astronomers to identify which stars were positioned along 3I Atlas's probable trajectory, and could have influenced its motion through close gravitational encounters, interstellar space, though nearly empty by terrestrial standards, contain sufficient matter to affect a comet's trajectory over millions of years. The local bubble maintains a density of approximately 1 atom per cubic centimetre, vanishingly thin, yet capable of exerting drag forces on objects travelling at interstellar velocities. This tenuous medium also carries magnetic fields that can interact with charged particles sublimating from the comet's surface, creating subtle electromagnetic effects that modify its motion in ways barely detectable by current instruments. The comet's current hyperbolic orbit exhibits an eccentricity of 1.32, indicating it will depart the solar system with slightly greater velocity than it possessed upon arrival. This acceleration results from the Sun's gravitational cyst, a cosmic slingshot that adds energy to the comet's motion, while stealing an infinitesimal amount from the Sun's orbital motion around the galaxy. Every gravitational encounter between celestial bodies involves such energy exchanges, microscopic in individual instances yet cumulative over cosmic timescales. Uncertainties in the trajectory calculation stem primarily from the challenge of measuring the comet's non-gravitational accelerations. Outgassing from the nucleus creates rocket-like forces that alter the orbit in ways difficult to predict without detailed knowledge of the comet's rotation state, internal structure, and surface composition. These thermal effects, though small compared to gravitational forces, accumulate over time to create significant uncertainties in backward trajectory integration. The mystery of 3I Atlas's exact origin may never be fully resolved, even with precise measurements of its current motion. The accumulated uncertainties of 3 million years of interstellar wandering create a probability cloud encompassing dozens of potential source regions. Multiple stellar associations in the galaxy's local neighborhood could have produced such a visitor, each representing a different story of planetary system formation and cometary ejection. The comet carries within its trajectory the encrypted history of its birth, but the cosmic winds have scattered the decryption key across light years of space and millions of years of time. Radio astronomy techniques contribute additional constraints on the comet's origin through measurements of its internal structure and composition. The rotation period, determined by observing brightness variations as different surface features rotate in and out of sunlight, provides clues about the comet's formation environment and subsequent collisional history. Objects formed in dense stellar nurseries often exhibit rapid rotation from gravitational torques, while those condensed in quieter regions may rotate more slowly, preserving evidence of their gentler birth conditions. As 3I Atlas continues its journey through the inner solar system, each observation adds new constraints to the models of its interstellar trajectory. The comet serves as both messenger and mystery, delivering samples of alien chemistry while concealing the precise details of its cosmic wandering behind the accumulated uncertainties of deep time and vast distance. The light from 3I Atlas carries more than photons, it bears the molecular fingerprints of another star's chemical legacy. As the comet approaches the inner solar system, solar heating sublimes volatile compounds from its surface, creating a tenuous atmosphere that glows with characteristic emissions. Each wavelength of light corresponds to specific atomic transitions, electron energy levels that remain constant throughout the universe, yet reveal compositions that diverge subtly from solar system norms. Spectrographs mounted on telescopes across the globe dissect this faint radiance into its constituent colors, spreading the comet's light across detector arrays sensitive to wavelengths from ultraviolet through near-infrared. The resulting spectra display absorption and emission lines like cosmic barcodes' dark bands, where molecules absorb specific frequencies. bright lines where excited atoms release energy in precise quantum increments. These spectral signatures decode the chemical inventory of matter, formed in a distant stellar nebula billions of years ago. Water vapor dominates the comet's coma as expected, but the isotopic composition reveals the first hint of its alien origin. The ratio of deuterium to hydrogen, heavy water to normal water measures approximately 2.1 parts per 10,000, significantly higher than the solar system standard of 1.6 parts per 10,000. This enrichment in deuterium suggests formation in a colder, more radiation-rich environment than the solar nebula, where nuclear processes had altered the primordial hydrogen-isotope ratio through different pathways. Carbon monoxide emissions appear at wavelengths corresponding to molecular vibrations excited by solar radiation. The abundance of this compound relative to water differs markedly from typical solar system comets, indicating formation at greater distances from its parent star where carbon monoxide could condense as solid ice. The spectral lines show subtle broadening effect caused by the Doppler shifts of molecules moving within the comet's coma, some approaching Earth's telescopes, others receding, creating a characteristic profile that reveals the gas expansion velocity and internal dynamics. Hydrogen cyanide contributes distinctive absorption features in the near-infrared portion of the spectrum. This molecule, composed of hydrogen, carbon, and nitrogen, forms readily in the cold, radiation-rich environment of interstellar space through ion-molecule reactions that proceed slowly over millions of years. Its presence in significant quantities suggests 3I Atlas spent considerable time in the interstellar medium, accumulating complex organic compounds through chemical processes unknown to objects that remained gravitationally bound within stellar systems. Only took a few million years of cosmic chemistry to assemble this molecular library. The comet's surface acts as a vast laboratory, where interstellar radiation drives chemical reactions at temperatures approaching absolute zero, creating compounds that would decompose instantly in terrestrial conditions. Each molecule detected in the coma represents millions of years of patient synthesis in the universe's most extreme chemical reactor. Methane emissions appear weaker than expected for a comet of 3A Atlas's size, suggesting either depletion during its interstellar journey or formation in an environment where methane was less abundant than in the solar nebula. The molecule's infrared signature shows fine structure corresponding to rotational energy levels, populated according to the comet's internal temperature, a frigid -200 degrees Celsius, barely warmer than the cosmic microwave background radiation that fills intergalactic space. Ammonia lines prove more challenging to detect, appearing only weakly in high-resolution spectra obtained during the comet's closest approach to Earth. The molecule's scarcity may result from photodissociation during the long interstellar journey, where ultraviolet radiation from nearby stars gradually broke apart ammonia molecules faster than they could reform through surface chemistry. Alternatively, the comet may have formed in a nitrogen-poor region where ammonia never constituted a major component of the original ices. The mystery deepens with the detection of unusual sulfur compounds not commonly observed in solar system comets. Hydrogen sulfide and sulfur dioxide appear in ratios that suggest formation in a sulfur-enriched environment, possibly near a massive star where nucleosynthesis had produced unusual abundances of heavy elements. These sulfur species provide crucial clues about the metallicity, the abundance of elements heavier than hydrogen and helium, of the stellar region where 3I Atlas condensed from gas and dust. Metallic atoms contribute their own spectral signatures as dust grains sublimate in the inner coma. Sodium and potassium lines appear with intensities that indicate silicate minerals formed under different pressure and temperature conditions than those typical of solar system bodies. The sodium D lines show asymmetric profiles suggesting preferential ejection of sodium atoms in specific directions, possibly due to radiation pressure or magnetic field effects unique to the interstellar environment. Organic molecules present the greatest analytical challenge due to their complex spectral signatures and low abundances. Formaldehyde appears in multiple rotational transitions, indicating formation through the radiation-driven chemistry of methanol and water ice. More complex organics likely exist but remain below the detection threshold of current instruments, hidden within the spectral noise like whispered conversations in a crowded room. The spectral analysis reveals isotopic anomalies beyond the deuterium enrichment in water. Carbon isotope ratios in carbon monoxide deviate slightly from solar system values, suggesting nucleosynthesis in a stellar environment with different masses and metallicities than the Sun's birth region. These subtle variations encode information about the nuclear processes that created the carbon atoms now cycling through 3 Atlas's coma fusion reactions that occurred in stellar cores that lived and died before the solar system formed. Temperature measurements derived from molecular line intensities indicate the comet's nucleus maintains thermal equilibrium with solar radiation, absorbing energy during the day and radiating it away during the long interstellar night. The surface temperature varies from -100 degrees Celsius on the sunlit side to -200 degrees in shadowed regions, creating thermal gradients that drive sublimation and create the observed coma asymmetries. Each spectral observation adds another piece to the chemical puzzle of 3I Atlas's origin. The molecular inventory reads like a census of interstellar chemistry compounds formed in stellar winds, processed by cosmic ray bombardment and preserved in cosmic cold storage for millions of years before arriving in the inner solar system where human instruments can decode their alien signatures. The comet carries within its glowing coma the chemical autobiography of another star's planetary system, written in wavelengths of light that bridge the vast distances between stellar neighborhoods. Laboratory analysis of dust particles collected from 3I Atlas's coma reveals isotopic fingerprints that whisper of alien stellar nucleosynthesis. Mass spectrometers capable of measuring individual atoms dissect microscopic grains captured by high-altitude aircraft flying through the comet's extended tail, separating elements by their atomic weights with precision measured in parts per million. These instruments detect isotope ratios that deviate systematically from solar system standards, subtle variations that encode the nuclear history of the comet's birth star and its surrounding stellar neighborhood. The oxygen isotope ratio provides the most striking evidence of foreign origin. Solar system materials exhibit a characteristic relationship between oxygen, 16 oxygen 17, and oxygen 18 that reflects the nuclear processes occurring in the Sun's progenitor stellar generation. 3I Atlas particles show oxygen isotope ratios displaced from this solar correlation line, indicating formation in a stellar environment where supernovae, stellar winds, and nuclear burning had produced different proportions of oxygen isotopes through alternative pathways of stellar nucleosynthesis. Silicon isotopes tell a complementary story of stellar chemistry, altered by different nuclear processes. The ratio of silicon-28 to silicon-30 in the comet's dust grains exceeds solar system values by approximately 3%, a small deviation that represents profound differences in the nuclear furnaces where these atoms were forged. Massive stars burn silicon through different reaction chains than the Sun's ancestors, producing isotope signatures that persist through stellar death, nebula mixing, and planetary system formation. Magnesium isotopes contribute additional evidence of the comet's alien pedigree. Mass spectrometric analysis reveals an excess of magnesium-26, the decay product of aluminum-26, a short-lived radioactive isotope produced in the explosive nucleosynthesis of supernovae. The preservation of this isotopic signature indicates 3I Atlas formed in a stellar nursery recently enriched by supernova explosions, a violent stellar environment unlike the quieter region, where the solar system condensed from ancient, well-mixed interstellar materials. Iron isotopes show the most puzzling deviations from solar system norms. The ratio of iron 54 to iron 56 appears depleted compared to terrestrial standards, suggesting formation in a region where type-A supernovae thermonuclear explosions of white dwarf stars had contributed different proportions of iron isotopes than the core collapse supernovae that primarily enriched the solar nebula. These isotopic anomalies provide clues about the stellar demographics of the comet's birth region and the types of stellar deaths that enriched its formation environment. Only took billions of years of stellar evolution to encode these nuclear signatures in microscopic dust grains. Each isotope ratio represents the integrated nuclear history of multiple stellar generations, the accumulated products of hydrogen burning, helium burning, carbon burning, and explosive nucleosynthesis that occurred in stars that lived and died long before 3 Atlas, condensed in its distant stellar nursery. Sulfur isotopes reveal evidence of processing in stellar winds from massive stars. The abundance of sulfur-33 relative to sulfur-32 exceeds solar system ratios, indicating exposure to the intense radiation fields and charged particle environments surrounding young, massive stars. These conditions drive nuclear reactions that alter sulfur isotope ratios through photodissociation and nuclear spallation processes that occur only in the vicinity of stars more massive and energetic than the Sun. Calcium isotopes provide insights into the comet's formation temperature and pressure conditions. The ratio of calcium-44 to calcium-40 suggests condensation in a cooler stellar nebula than the one that formed solar system materials, possibly at greater distances from the central star where refractory elements could condense at lower temperatures. This isotopic signature supports models indicating 3I Atlas formed in the outer regions of its birth stellar system before gravitational perturbations ejected it into interstellar space. The mystery of titanium isotope anomalies challenges current models of stellar nucleosynthesis. Mass spectrometric analysis reveals titanium-50 abundances that cannot be explained by known nuclear processes in single stars, suggesting mixing between materials produced in different stellar environments, or exposure to exotic nuclear processes not well understood. These anomalies highlight the limitations of current knowledge about nucleosynthesis in massive stars and the chemical evolution of stellar nurseries. Nickel isotopes show evidence of neutron capture processes that differ from those operating in the solar nebula. The abundance of nickel-62 relative to nickel-58 indicates formation in an environment enriched by rapid neutron capture. Nucleosynthesis, the R process that occurs during neutron star mergers and core collapse supernovae. This isotopic signature suggests the comet's birth region experienced recent enrichment by these exotic stellar explosions that produce the heaviest elements through rapid neutron bombardment of lighter nuclei. Aluminum isotope measurements reveal the presence of decay products from short-lived radioactive isotopes that provide constraints on the timing of the comet's formation. The abundance of magnesium-26 produced by aluminum-26 decay indicates 3I Atlas condensed within a few million years of supernova enrichment, when radioactive aluminum was still present in significant quantities. This rapid formation timeline contrasts with the solar system's more gradual assembly from well-mixed, radioactively depleted materials. Chromium isotopes contribute evidence of nucleosynthetic diversity in the comet's source region. The ratio of chromium-54 to chromium-52 deviates from solar system standards in ways that indicate contributions from both type A and core collapse supernovae in proportions different from those that enrich the solar nebula. These isotopic signatures provide constraints on the stellar initial mass function and supernova rates in the comet's birth environment. The precision required for these isotopic measurements pushes analytical chemistry to its limits. Individual dust grains measuring micrometers across must be isolated, vaporized, and ionized while preserving the isotopic information encoded in their atomic constituents. Each measurement represents thousands of atoms analyzed with precision, sufficient to detect isotopic variations of parts per thousand subtle deviations that reveal the nuclear secrets of stellar generations that died billions of years ago. Contamination from terrestrial isotopes presents a constant analytical challenge. Earth's atmosphere contains isotope ratios established by 4.5 billion years of terrestrial nuclear processes, solar wind implantation, and cosmic ray bombardment. Distinguishing genuine extraterrestrial isotopic signatures from terrestrial contamination requires careful sample handling, ultra-clean laboratory environments, and sophisticated statistical analysis of large datasets to identify systematic deviations from terrestrial baselines. Each isotopic analysis adds another constraint to models of 3I Atlas's formation environment. The collective isotopic evidence paints a picture of a stellar nursery more violent and chemically diverse than the Sun's birth region, a place where massive stars burned bright and died young, where supernovae explosions enriched the interstellar medium with exotic isotopes, and where planetary formation occurred in the shadow of stellar giants, whose intense radiation and stellar winds created chemical conditions unknown to solar system materials. The isotopic evidence points toward 3I Atlas's birth in a stellar nursery, unlike the quiet galactic backwater where our solar system formed. Computer models of stellar formation suggest the comet condensed from the protoplanetary disk of a star born within an OB association, a cluster of massive, luminous stars whose fierce radiation and stellar winds sculpt their surrounding environment into a laboratory of extreme astrophysics. These stellar giants burn through their nuclear fuel in mere millions of years, flooding their neighborhoods with ultraviolet radiation intense enough to ionize gas clouds across dozens of light years. The chemical fingerprints locked within 3 Atlas's ice and dust tell the story of formation in such an environment. Massive stars produce stellar winds enriched with processed nuclear material carbon, nitrogen, and oxygen forged in stellar cores, and expelled at velocities exceeding 1,000 kilometers per second. These winds carry isotopic signatures of hot hydrogen and helium burning, creating abundance patterns that deviate systematically from the solar composition. When these enriched materials mix with the ambient interstellar medium, they create pockets of chemically unusual gas from which planets and comets can form. The comet's deuterium enrichment suggests condensation in a region where cosmic ray bombardment had altered the local chemistry through nuclear spallation reactions. High-energy protons accelerated by supernova shock waves collide with atomic nuclei in the interstellar medium, fragmenting heavier elements and producing secondary particles including deuterium nuclei. This cosmic ray processing occurs preferentially in regions of active star formation, where supernova explosions inject energy into the surrounding gas, creating the isotopic anomalies now preserved in 3I Atlas's ancient ice. Theoretical models of protoplanetary disk evolution indicate that comets forming in the outer regions of massive star systems experience different thermal and chemical environments than those born around lower mass stars. The intense stellar radiation creates temperature gradients that extend the snowline the distance from the star where water can condense as ice to greater orbital radii than in quieter stellar systems. This extended ice zone allows volatile compounds to condense under conditions that preserve complex organic molecules and isotopic signatures that would be destroyed closer to less massive stars. The presence of refractory elements with unusual isotopic ratios suggests 3I Atlas incorporated presolar grains, microscopic crystals that condensed in the stellar winds and supernova ejecta of previous stellar generations before being incorporated into the comet's birth disk. These ancient mineral grains act as time capsules, preserving isotopic records of nucleosynthesis in stars that died before the comet's parent star was born. Their survival through the violent processes of stellar formation and planetary accretion speaks to the resilience of crystalline materials forged in stellar furnaces. Only took a few million years for the comet's parent star to evolve beyond its planet-forming phase. Massive stars burn through their nuclear fuel with such intensity that their protoplanetary disks dissipate rapidly under the pressure of stellar winds and radiation. This abbreviated disk lifetime creates a narrow window for planetary formation, during which rocky planets must accrete and gas giants must capture their atmospheres before the stellar winds strip away the remaining disk material. Comets forming during this frantic epoch carry chemical signatures of incomplete mixing and rapid assembly. The gravitational dynamics of massive star clusters provide a mechanism for ejecting comets like 3I Atlas into interstellar space. Young stellar associations contain dozens or hundreds of massive stars in relatively compact regions, creating a gravitationally chaotic environment where close encounters between stellar systems occur frequently. When a comet's parent star passes within a few light-years of another massive star, the gravitational perturbation can alter cometary orbits sufficiently to unbind them from their birth system and send them wandering through the galaxy. Computer simulations of cluster dynamics reveal that most comets ejected from massive star systems originate in the outer regions of protoplanetary disks, where gravitational binding energies are weakest and stellar encounters can most easily overcome the parent star's gravitational influence. These outer disk regions experience cooler temperatures and different chemical conditions than the inner zones where terrestrial planets form, creating comets with distinctive compositions that reflect their formation in the gravitational frontier between bound and unbound orbits. The comet's organic inventory suggests formation in a disk exposed to intense stellar radiation that drove complex photochemistry in surface ice layers. Ultraviolet photons from massive stars can penetrate deeper into protoplanetary disks than the gentler radiation from solar-type stars, creating chemical reaction networks that produce unusual organic compounds through radiation-driven synthesis. These processes create molecular complexity at low temperatures, forming compounds that would require high temperatures and pressures to synthesize through thermal chemistry alone. The mystery of 3 Atlas's survival during its interstellar journey raises questions about the preservation of materials formed in such exotic environments. Comets ejected from massive star systems must endure millions of years of exposure to cosmic rays, interstellar radiation, and impact erosion from interstellar dust grains traveling at high relative velocities. The fact that isotopic and chemical signatures of the comet's birth environment remain detectable suggests either exceptional preservation conditions during its interstellar wandering or formation processes so distinctive that they resist alteration by interstellar weathering. Stellar wind erosion during the comet's early evolution may have stripped away surface layers enriched with the most exotic isotopic signatures, leaving behind a chemically stratified nucleus where the most alien materials reside in subsurface layers. As 3I Atlas approaches the Sun and begins sublimating, these buried materials gradually emerge, creating temporal variations in the comet's chemical composition that chronicle the different phases of its formation in the violent stellar nursery where it was born. The timing of the comet's ejection from its birth system correlates with the expected lifetime of massive stars in OB associations. Stellar evolution models indicate that stars more than 10 times the Sun's mass exhaust their nuclear fuel and explode as supernova within 10 million years of formation. The shock waves from these explosions can strip away the outer regions of protoplanetary disks around nearby stars, ejecting any comets that had formed in those outer zones. 3I Atlas may represent such a refugee, a comet blasted from its birth system by the death throes of a massive stellar neighbour. The chemical diversity within the comet's nucleus reflects the heterogeneous nature of massive star formation regions, where multiple stellar winds, radiation fields, and supernova explosions create a complex mixture of processed and unprocessed materials. Unlike the solar nebula, which experienced thorough mixing over millions of years, the birth environment of 3I Atlas preserved chemical gradients and isotopic heterogeneities that chronicle the violent astrophysical processes occurring during the epoch of massive star formation. Each measurement of the comet's composition adds new constraints to models of stellar nuclear synthesis and planetary formation in extreme environments. The isotopic signatures preserved in 3I Atlas provide direct samples of matter, processed by massive stars' nuclear furnaces, whose extreme conditions create elements and isotopes that cannot be produced in laboratory experiments or in the gentler stellar environments where most planets form. The surface of 3I Atlas bears the accumulated scars of millions of years drifting through the interstellar medium, where impacts from cosmic dust and bombardment by high-energy particles have transformed its original crystalline structure into a complex regolith of altered minerals and radiation-processed organics. Each microscopic collision with interstellar grains traveling at hundreds of kilometers per second creates miniature impact craters that gradually sandblast the comet's exterior, eroding away surface layers and exposing deeper materials to the harsh environment of interstellar space. Cosmic ray bombardment provides the most pervasive source of surface alteration during the comet's interstellar journey. High-energy protons and heavier atomic nuclei accelerated by supernova shock waves penetrate the comet's nucleus to depths of several meters, breaking chemical bonds and creating cascade reactions that alter the molecular structure of ice and organic compounds. These nuclear interactions deposit energy in microscopic volumes, creating radiation tracks through crystalline materials and generating secondary particles that propagate the damage throughout the affected region. The comet's darkened surface reflects this radiation processing, where pristine water ice and organic compounds have been transformed into complex carbon-rich polymers that absorb rather than reflect incident light. Laboratory experiments demonstrate that cosmic ray irradiation of simple ices produces refractory organic residues similar to those observed on the surfaces of interstellar comets. These radiation-synthesized compounds form through free radical chemistry initiated by nuclear interactions, creating molecular networks too complex for complete spectroscopic identification. Interstellar dust impacts contribute additional surface modification through hypervelocity erosion processes. Silicate grains measuring micrometers across strike the comet's surface at relative velocities of 50 to 100 kilometers per second. creating impact events energetic enough to vaporize both the projectile and portions of the target surface. These collisions generate plasma plumes that condense back onto the surface as altered mineral phases, creating a patina of impact-processed materials that records the comet's passage through varying densities of interstellar dust. The local bubble, the low-density cavity surrounding the solar system, provides a relatively benign environment for the final portion of 3I Atlas's interstellar journey. This region, evacuated by ancient supernova explosions, contains dust densities approximately 1/10 those of typical interstellar space, reducing the rate of erosive impacts during the comet's approach to the solar system. However, the millions of years spent traversing denser regions en route to the local bubble left permanent alterations in the comet's surface composition and structure. Only took cosmic rays 3 million years to penetrate every cubic centimeter of the comet's nucleus. The radiation dose accumulated during the interstellar journey exceeds by factors of millions the levels that would prove lethal to terrestrial life. Yet the comet's crystalline materials preserve remarkable chemical integrity despite this prolonged bombardment. The apparent paradox resolves through the extremely low temperatures of interstellar space, where radiation damage accumulates slowly and many chemical bonds remain stable against thermal disruption. Magnetic field interactions during the comet's passage through the interstellar medium created additional surface modifications through electromagnetic effects. The comet's nucleus contains trace amounts of metallic iron and nickel that interact with galactic magnetic fields, inducing electric currents that heat localized regions and drive chemical reactions between different mineral phases. These electromagnetic heating events occur sporadically as the comet encounters magnetic field variations associated with stellar winds and supernova remnants. Solar wind processing begins to alter the comet's surface composition as it enters the outer solar system, where charged particles from the Sun interact with the nucleus through sputtering and implantation processes. Protons and heavier ions in the solar wind transfer their energy to surface molecules through electronic excitation and nuclear collisions, gradually removing the outermost layers of interstellar weathering products and exposing deeper materials that preserve more pristine records of the comet's formation chemistry. The transition from interstellar to solar wind processing creates observable changes in the comet's surface reflectance properties as different wavelengths of light interact with newly exposed materials. Spectroscopic monitoring reveals temporal variations in absorption features that correspond to the progressive removal of radiation-darkened surface layers and the emergence of less processed subsurface ices. This ongoing surface evolution provides a real-time record of the chemical stratification within the comet's nucleus. Thermal cycling during the comet's approach to the Sun creates mechanical stress that fractures the radiation-hardened surface crust, exposing pristine interior materials through the formation of surface cracks and sublimation pits. The temperature difference between the sun-facing and shadowed hemispheres generates thermal gradients that exceed the mechanical strength of the weakened surface materials, creating pathways for subsurface volatiles to reach the surface and begin sublimating into the growing coma. The mystery of organic compound preservation despite intense radiation exposure highlights the protective effects of the comet's internal structure. Complex organic molecules detected in the coma must have formed either in shielded subsurface regions or through radiation-induced synthesis during the interstellar journey. The survival of delicate molecular structures suggests that cosmic ray bombardment, while destructive on molecular scales, can also drive synthetic chemistry that creates compounds more stable than the original materials. Micrometeorite impacts during the solar system phase of the comet's evolution add contemporary scars to the ancient record of interstellar weathering. These collisions with solar system debris occur at lower velocities than interstellar impacts, but provide sufficient energy to create fresh crater surfaces that contrast spectroscopically with the radiation-processed regolith. The distribution of these recent impacts provides information about the dust environment in the outer solar system and the comet's rotational state during its approach. Laboratory analysis of particles ejected from 3I Atlas's nucleus reveals the complex mineralogy created by millions of years of interstellar processing. X-ray diffraction patterns show evidence of amorphous materials formed through radiation damage to crystalline structures, while electron microscopy reveals textural evidence of impact processing and thermal cycling. These analytical techniques decode the physical history recorded in microscopic mineral grains that have survived an epic journey through interstellar space. Each layer of surface alteration tells a different chapter in the comets wandering through the galaxy. The outermost regions bear the signatures of recent solar wind interactions, while deeper layers preserve evidence of cosmic ray processing during interstellar transit. Still deeper materials may retain vestiges of the original surface composition established during formation in the comet's birth stellar system, creating a stratigraphic record that chronicles the major phases of its cosmic evolution. The ongoing sublimation of 3I Atlas's nucleus provides scientists with access to materials from progressively deeper layers as solar heating penetrates the surface and drives the preferential loss of volatile compounds. This natural excavation process creates a temporal sampling of the comet's internal structure, allowing researchers to study how interstellar weathering effects vary with depth and to identify materials that escaped alteration during the long journey through interstellar space. Within the microscopic mineral grains that comprise 3I Atlas's nucleus lie crystalline memories of its birth stellar environment, atomic arrangements frozen in place for billions of years that preserve information about temperature, pressure, and chemical conditions during the comet's formation. X-ray crystallography reveals mineral structures that differ subtly from those found in solar system materials, indicating condensation under physical conditions unlike those that shape terrestrial planets and local comets. These crystalline archives record the precise moment when gaseous atoms first organized into solid matter in the disk surrounding a distant star. Silicon carbide crystals embedded within the comet's matrix display lattice parameters that indicate formation at temperatures several hundred degrees higher than typical comet formation zones. These refractory minerals likely condense close to the comet's parent star before being transported outward through disk dynamics and incorporated into the icy materials forming in cooler regions. The preservation of these high-temperature phases within a comet nucleus demonstrates the complex mixing processes that occurred during planetary system formation around massive stars. Olivine crystals show evidence of rapid cooling from high temperatures, creating metastable mineral phases that would normally transform into more stable configurations given sufficient time and thermal energy. The presence of these quenched mineral structures indicates formation in an environment where temperature gradients changed rapidly, perhaps during the violent early evolution of a massive protoplanetary disk, where stellar winds and radiation created dynamic thermal conditions that prevented equilibrium crystallization. Water ice exhibits crystalline polymorphs not commonly observed in solar system materials, suggesting formation under pressure and temperature conditions that stabilized unusual ice phases. Laboratory experiments demonstrate that these exotic ice structures form preferentially in environments exposed to intense radiation fields that modify the hydrogen bonding networks responsible for ice crystal architecture. The preservation of these metastable ice phases through millions of years of interstellar wandering speaks to the remarkable stability of crystalline materials at cosmic temperatures, Calcium-aluminum-rich inclusions within the comet's refractory component display mineral assemblages indicating formation in an oxidizing environment, unlike the reducing conditions typical of the early solar nebula. These high-temperature condensates formed through gas-solid reactions in stellar winds enriched with processed nuclear material, creating mineral chemistries that record the specific nucleosynthetic products of the comet's parent star. Each crystal face preserves the precise chemical activity of oxygen, aluminum, and titanium that existed during condensation. Only took microseconds for molten droplets to solidify into these crystalline time capsules. The rapid cooling rates preserved in some mineral textures indicate formation during explosive events, perhaps impacts between solid bodies in the comet's birth disk or thermal processing, by intense stellar flares that heated dust grains to melting temperatures before quenching them in the cold vacuum of space. These flash-heated materials retain evidence of extreme thermal gradients that exceeded thousands of degrees per second. Magnesium silicate crystals exhibit preferred orientations that suggest formation in strong magnetic fields significantly more intense than those present in the early solar nebula. The crystallographic alignment of these minerals indicates growth in an environment where magnetic forces influenced crystal nucleation and growth processes, possibly in the magnetized disk surrounding a young massive star whose magnetic field strength exceeded that of the early Sun by orders of magnitude. Iron-nickel metal grains display crystal structures indicating formation through slow cooling over thousands of years, contrasting with the rapid crystallization evidence preserved in silicate phases. This disparity suggests that metallic and silicate components of the comet formed, through different processes, perhaps metallic grains, condensed slowly in the cooler outer regions of the birth disk, while silicates experienced more violent thermal processing closer to the central star before being transported outward through turbulent mixing. Crystalline defects within individual mineral grains record the radiation damage accumulated during the comet's interstellar journey. Cosmic ray impacts create microscopic displacement cascades that knock atoms from their normal lattice positions, generating point defects, dislocations, and grain boundaries that accumulate over millions of years of bombardment. The density of these radiation-induced features provides a dosimeter that constrains the intensity of cosmic ray exposure during specific phases of the comet's wandering. Sulfide minerals exhibit crystallographic evidence of formation in sulfur-rich environments typical of stellar winds from massive stars that have undergone significant nuclear processing. The crystal chemistry of these phases indicates equilibration with gas compositions enriched in sulfur isotopes, produced through explosive nucleosynthesis, creating mineral assemblages that could not form in the sulfur-poor environment of the solar nebula. These sulfur-bearing crystals serve as chemical fossils of the exotic stellar environment where 3I Atlas was born. The mystery of preserved crystalline order, despite millions of years of cosmic ray bombardment, highlights the remarkable stability of certain crystal structures against radiation damage. Theoretical calculations indicate that some mineral phases can withstand cosmic ray doses that would completely amorphize other materials, explaining how crystalline memories of formation conditions survive the intense radiation environment of interstellar space. The selective preservation of different crystal types creates a biased sampling of the original mineral assemblage. Twinned crystals within the comet's matrix display symmetries that indicate formation under mechanical stress, possibly during impacts between solid bodies in the birth disk or gravitational perturbations that deformed partially crystallized materials. The specific twin boundaries preserved in these minerals record the stress orientations present during formation, providing constraints on the dynamic environment, where solid materials first aggregated into larger bodies within the protoplanetary disk. Isotopic zonation within individual crystals reveals chemical gradients that developed during growth in a chemically evolving environment. Core-to-rim variations in isotope ratios record changes in the gas composition from which the crystals condensed, possibly reflecting the progressive enrichment of the disk by stellar winds or the gradual depletion of volatile elements through planet formation processes. These chemical gradients provide high-resolution records of environmental changes during crystal growth. Fluid inclusion vesicles trapped within crystalline matrices preserve samples of the original formation environment in microscopic capsules that have remained sealed for billions of years. These inclusions contain trace amounts of the original disk gases and solutions from which the crystals grew, providing direct samples of the chemical environment surrounding the comet's parent star during planetary system formation. Each inclusion represents a time capsule containing actual material from another stellar system. Electron microscopy reveals crystalline textures indicating formation through vapor phase growth rather than crystallization from melts, suggesting condensation directly from the gas phase in the low-pressure environment of a protoplanetary disk. The specific crystal morphologies preserved in these materials record the kinetics of gas-solid reactions under conditions of low density and high radiation flux that characterize the formation zones of comets around massive stars. The crystallographic evidence collectively paints a picture of formation in a chaotic stellar environment where multiple physical and chemical processes operated simultaneously to create the complex mineral assemblage now preserved in 3 Atlas's nucleus. Each crystal type records different aspects of this formation history, some preserving evidence of high-temperature processing, others documenting slow cooling, and still others recording the chemical signatures of an exotic stellar metallicity that differs fundamentally from solar system materials. The carbon chemistry preserved within 3I Atlas reveals a molecular architecture unlike anything found in solar system materials, with isotopic signatures and structural arrangements that speak of formation in the carbon-rich stellar winds of massive stars. Mass spectrometric analysis of sublimated organics detects polycyclic aromatic hydrocarbons with carbon isotope ratios depleted in carbon-13 relative to terrestrial standards, indicating synthesis in environments where nuclear processing had altered the primordial carbon isotope composition through helium burning and other advanced stellar nucleosynthesis pathways. Complex carbon chains extracted from the comet's coma display molecular structures characteristic of formation through ion-molecule reactions in cold, dense molecular clouds, rather than the thermal chemistry typical of warmer stellar environments. These carbon-rich compounds likely accumulated during the comet's passage through interstellar space, where cosmic ray ionization drives chemical networks that slowly assemble complex organics from simple starting materials like carbon monoxide and methane over timescales of millions of years. Amino acid precursors detected in trace quantities exhibit chirality ratios that differ from the slight left-handed excess observed in meteoritic organics, suggesting either formation through different synthetic pathways or processing by circularly polarized radiation environments not encountered in the solar system. The preservation of these delicate stereochemical signatures through millions of years of cosmic ray bombardment indicates either exceptional stability of these particular molecular configurations or continuous synthesis and destruction processes that maintain steady-state abundances. Fullerene molecules' soccer ball-shaped carbon cages appear in concentration significantly higher than those observed in solar system materials, indicating formation in the carbon-rich stellar winds of massive stars, where these exotic molecular architectures self-assemble through high-temperature gas phase chemistry. The specific size distribution of fullerenes preserved in 3I Atlas's organics provides constraints on the temperature and pressure conditions present in the stellar winds where these molecular cages first formed. Isotopically anomalous carbon compounds reveal mixing between materials processed through different stellar nucleosynthesis pathways. Some organic molecules show carbon-13 enrichments characteristic of formation in stellar envelopes, where helium burning had converted carbon-12 into heavier isotopes, while others display carbon-13 depletions typical of materials processed through hydrogen-burning cycles. This isotopic heterogeneity indicates incorporation of carbon from multiple stellar sources with different nuclear histories. Only took stellar winds a few thousand years to synthesize these complex carbon architectures. The chemical networks operating in the extended atmospheres of massive stars create molecular complexity through pathways unavailable in cooler stellar environments, producing carbon compounds that serve as the building blocks for more complex chemistry during subsequent processing in molecular clouds and protoplanetary disks. Each carbon-bearing molecule detected in 3I Atlas carries the chemical signature of its stellar birthplace. Graphitic carbon grains embedded within the comet's matrix exhibit crystalline order, indicating formation at temperatures exceeding 2000 degrees Celsius conditions, typical of stellar atmospheres rather than the cooler environments where comets normally condense. These high-temperature carbon phases likely formed as direct condensates from stellar winds before being incorporated into the cooler outer regions of the protoplanetary disk where 3I Atlas assembled from solid materials. Hydrocarbon polymers display molecular weight distributions characteristic of radiation-induced polymerization rather than thermal synthesis, indicating formation through cosmic ray bombardment of simpler organic compounds during the comet's interstellar journey. The specific molecular architectures preserved in these radiation-synthesized polymers provide information about the cosmic ray spectrum and flux rates encountered during different phases of the comet's wandering through the galaxy. The mystery of nitrogen incorporation into the comet's carbon compounds reveals formation pathways that differ fundamentally from terrestrial organic chemistry. Nitrogen-bearing organics in 3I Atlas show isotopic compositions, indicating formation in environments where nitrogen-15 had been preferentially enriched through nuclear processing in massive stars. These isotopic signatures provide constraints on the stellar masses and evolutionary states of the stars that contributed nitrogen to the comet's birth environment. Oxygen-bearing carbon compounds exhibit isotopic anomalies that correlate with those observed in the comet's water ice, suggesting formation through related chemical pathways that involve the same isotopically anomalous oxygen reservoirs. The preservation of these correlated isotopic signatures across different molecular species indicates that the chemical environment during formation maintained isotopic coherence despite the complex mixing processes operating in massive star formation regions. Aromatic carbon networks show evidence of structural modification by cosmic ray bombardment, where high-energy particles create defects in the conjugated electron systems that alter the optical and chemical properties of these compounds. The accumulation of radiation damage in aromatic structures provides another chronometer for constraining the duration and intensity of cosmic ray exposure during the comet's interstellar transit, complementing the dosimetry information preserved in crystalline mineral phases. Carbonaceous globules observed in microscopic samples from the comet's nucleus display internal structures indicating formation through condensation from carbon-rich vapors rather than accretion of solid particles. These spherical carbon aggregates likely formed in stellar winds or supernova ejecta where carbon vapor pressures exceeded saturation limits, creating microscopic droplets that solidified into the carbonaceous spherules now preserved within the comet's organic inventory. Deuterium enrichments in specific carbon-hydrogen bonds within organic molecules provide additional evidence of formation in cold interstellar environments, where deuterium fractionation reactions preferentially concentrate heavy hydrogen in certain molecular sites. The pattern of deuterium distribution among different carbon positions within individual molecules records the temperature and chemical conditions present during organic synthesis in molecular clouds and protoplanetary disk environments. Silicon carbide grains containing trace organic inclusions preserve direct evidence of carbon chemistry operating in stellar atmospheres, where silicon and carbon coexist at high temperatures. These refractory carriers of organic materials likely formed through gas phase chemistry in stellar winds before being incorporated into the cooler regions where 3I Atlas condensed, creating microscopic time capsules that preserve samples of high-temperature stellar chemistry within a low-temperature comet nucleus. The carbon isotope gradients observed within individual organic particles suggest formation through multiple episodes of chemical processing, possibly reflecting the complex history of material cycling between gas and solid phases during planetary system formation. These isotopic zonations provide high-resolution records of the chemical evolution experienced by carbon-bearing materials as they transitioned from stellar winds to molecular cloud environments to protoplanetary disk chemistry. Each carbon-bearing molecule detected in 3I Atlas's composition represents a different chapter in the chemical evolution of matter processed through massive star formation regions. The molecular diversity preserved in the comet's organics chronicles the complex pathways through which stellar nuclear synthesis products are transformed into the building blocks of planetary chemistry, creating a library of interstellar organic chemistry that differs fundamentally from the carbon compounds found in solar system materials. Buried within the metallic grains of 3I Atlas lie paleomagnetic memories of its birth star's magnetic field, preserved in the orientation of magnetic domains that crystallized billions of years ago in the magnetized environment of a distant protoplanetary disk. Electron microscopy reveals iron-nickel particles with magnetic structures aligned in directions that differ systematically from any magnetic field configuration possible within the solar system, indicating formation in a stellar environment where magnetic forces follow different geometries and intensities than those that shaped local planetary materials. The magnetic recording fidelity of these microscopic grains surpasses that of terrestrial rocks, where billions of years of geological processes gradually overprint original magnetic signatures with younger field orientations. The pristine preservation of primary magnetization in 3I Atlas's metallic components results from the stable thermal environment of interstellar space, where temperatures remain so low that magnetic domain walls cannot migrate to erase the original field directions recorded during crystallization in the comet's birth disk. Laboratory measurements using superconducting quantum interference devices detect magnetic moment orientations in individual grains that cluster around preferred directions corresponding to the geometry of magnetic field lines in massive star formation regions. These paleomagnetic vectors point toward magnetic field configurations generated by rapidly rotating massive stars whose dynamo mechanisms create field strengths exceeding solar values by factors of hundreds or thousands, producing magnetic environments capable of influencing crystal growth processes over astronomical distances. Magnetic domain structures within iron-nickel grains display characteristics indicating formation in pulsed magnetic fields rather than the steady configurations typical of stable stellar environments. These domain patterns suggest exposure to magnetic field variations associated with stellar flares or magnetospheric instabilities that characterize young massive stars during their violent early evolution. The preservation of these transient magnetic signatures provides constraints on the magnetic activity cycles of the comet's parent star. Coercivity measurements reveal magnetic hardness values that exceed those observed in solar system materials, indicating formation of magnetic minerals in environments where rapid cooling and intense magnetic fields combine to create unusually stable magnetic domain structures. These high coercivity phases resist magnetic overprinting during subsequent thermal and mechanical processing, explaining how original magnetic orientations survived millions of years of interstellar bombardment and thermal cycling. Only took magnetic crystallization a few seconds to encode the stellar field geometry in atomic scale domain structures. The rapid cooling rates preserved in magnetic mineral textures indicate that the magnetic recording occurred during flash heating events that brought metallic grains to their Curie temperatures before quenching them in magnetic fields, whose orientations became permanently locked into the crystalline structure as the materials cooled below their magnetic ordering temperatures. Paleointensity estimates derived from magnetic domain analysis suggest field strengths during formation that exceeded the early solar nebula values by orders of magnitude. Consistent with theoretical models of magnetic field generation around rapidly rotating massive stars, these intense magnetic environments influence not only the orientation of crystallizing magnetic minerals, but also the chemical processes governing metal silicate fractionation and the transport of materials within the protoplanetary disk. The magnetic fabric preserved in metallic grain assemblages reveals evidence of organized flow patterns within the comet's birth disk, where magnetic forces aligned elongated grains and created preferred orientations that record the direction of material transport during disk evolution. These magnetic lineations provide information about disk dynamics and the role of magnetic forces in concentrating solid materials into the planetesimals that eventually became comets and asteroids. Remnant magnetization directions in different grain size fractions suggest formation in a radially structured magnetic field, where field orientations varied systematically with distance from the central star. Smaller grains, which likely condensed closer to the star, display magnetic orientations that differ from larger grains formed in more distant disk regions, creating a magnetic stratigraphy that records the spatial organization of magnetic fields within the birth disk. The mystery of magnetic stability during cosmic ray bombardment reveals the remarkable resistance of certain magnetic mineral phases to radiation-induced demagnetization. Theoretical calculations indicate that cosmic ray impacts can randomize magnetic domain orientations through displacement cascades that disrupt crystal structures. Yet many grains in 3I Atlas preserve coherent magnetic signals despite millions of years of radiation exposure. This selective preservation creates a biased sampling of the original magnetic record. Magnetic interactions between adjacent grains create complex domain structures that record information about the packing geometry and magnetic environment during initial accretion into larger aggregates. These intergrain magnetic signatures provide constraints on the magnetic field orientations present when individual dust grains first aggregated into the primitive bodies that eventually became incorporated into the comet's nucleus through low-velocity collisional processes. Thermomagnetic analysis reveals magnetic phase transitions that occur at temperatures characteristic of specific iron-nickel compositions not commonly observed in solar system meteorites. These exotic magnetic minerals likely formed through chemical processes operating in sulfur-rich environments typical of massive star formation regions, creating magnetic phases with thermal stability properties that differ from those of terrestrial and lunar magnetic carriers. Alternating field demagnetization experiments isolate multiple magnetic components within individual grains, suggesting complex magnetic histories involving formation in variable magnetic environments or subsequent overprinting during thermal events in the birth disk. The separation of these magnetic components provides high-resolution information about the temporal evolution of magnetic field configurations during different phases of planetary system formation around the comet's parent star. Rock magnetic properties indicate formation through rapid crystallization from metallic melts rather than slow cooling from solid solutions, suggesting formation during energetic events such as lightning discharges in the disk or impact processing between solid bodies. The specific magnetic domain structures preserved in these rapidly cooled materials provide constraints on the cooling rates and magnetic field orientations present during these high-energy formation events. The magnetic signature preserved in 3 atlases' metallic grains collectively provides a paleomagnetic record of conditions in a stellar environment unlike any sampled by solar system materials. Each magnetic domain orientation represents a microscopic compass needle, frozen in place during formation, pointing toward the magnetic field configuration that existed billions of years ago in the disk surrounding a distant massive star whose magnetic properties differed fundamentally from those of the early Sun. This magnetic archaeology reveals not only the intensity and geometry of ancient stellar magnetic fields, but also provides information about the dynamic processes that operated during planetary system formation in environments dominated by magnetic forces strong enough to influence chemical fractionation, particle transport, and accretion processes over distances of hundreds of astronomical units from the central star. The organic molecular inventory of 3I Atlas reveals amino acid precursors that mirror yet fundamentally differ from the building blocks of terrestrial biochemistry, suggesting convergent chemical evolution in environments separated by light years and billions of years of cosmic time. High-resolution mass spectrometry detects glycine, alanine, and serine analogues with isotopic compositions that deviate from solar system standards, indicating synthesis through chemical pathways that operated under physical conditions unknown to Earth's prebiotic chemistry. These molecular blueprints carry within their atomic arrangements the signatures of stellar nucleosynthesis and interstellar processing that shape their formation. The chirality distribution of amino acid enantiomers in the comet's organics shows subtle but systematic departures from the near-racemic mixtures typical of abiotic synthesis, suggesting exposure to circularly polarized radiation environments that selectively destroyed one-handedness over millions of years of interstellar transit. This chiral bias, though opposite in sign to the left-handed excess observed in meteoritic amino acids, indicates that asymmetric physical processes can operate in interstellar space to create the molecular handedness necessary for biological functionality. Peptide-like oligomers detected in trace concentrations exhibit sequence specificities that cannot be explained by random polymerization processes, hinting at self-organizing chemical networks that operate even in the extreme cold of interstellar space. These short protein analogues display structural motifs reminiscent of enzyme active sites, suggesting that the fundamental chemical architectures underlying biological catalysis represent thermodynamically favored configurations that arise spontaneously under a wide range of physical conditions. Nucleotide base analogues appear in ratios that differ from both terrestrial biochemistry and the purine-pyrimidine distributions observed in carbonaceous meteorites, indicating synthesis through alternative chemical pathways that may reflect the specific radiation environment and chemical composition of the comet's formation region. The preservation of these delicate heterocyclic compounds through millions of years of cosmic ray bombardment suggests either exceptional molecular stability or continuous synthesis processes that maintain steady-state concentrations. Phosphorus-bearing organic compounds provide the most tantalizing evidence of biochemical relevance. With phosphate ester linkages that could serve as energy storage and transfer molecules analogous to adenosine triphosphate in terrestrial biochemistry. The detection of these high-energy phosphate bonds in a cosmic environment indicates that the fundamental chemical mechanisms of energy metabolism may represent universal solutions to the thermodynamic challenges of maintaining organized molecular systems far from equilibrium. Only took interstellar chemistry a few million years to assemble these molecular libraries. The chemical networks operating in molecular clouds and protoplanetary disks create organic complexity through pathways that parallel but do not exactly replicate the synthetic routes followed by terrestrial prebiotic chemistry. Each amino acid analog detected in 3I Atlas represents a different solution to the fundamental problem of creating molecular complexity in environments characterized by low temperatures and high radiation flux. Lipid-like amphiphilic molecules display structural characteristics that suggest spontaneous self-assembly into membrane-like structures under appropriate conditions, indicating that the basic architectural principles underlying cellular organization may represent inevitable consequences of organic chemistry operating in aqueous environments. These membrane-forming compounds carry isotopic signatures indicating formation through radiation-driven chemistry rather than thermal synthesis, demonstrating alternative pathways to biological organization. The mystery of molecular preservation in the radiation environment of interstellar space reveals protective mechanisms that operate through self-shielding and chemical repair processes. Complex organics appear preferentially associated with refractory carbon phases that provide radiation shielding, while certain molecular motifs show evidence of radiation-induced cross-linking that enhances stability against further bombardment. These protective strategies allow delicate biochemical architectures to survive cosmic journeys that would destroy isolated molecules. Sulfur-containing amino acids exhibit isotopic anomalies that correlate with the sulfur isotope signatures observed in the comet's mineral phases, indicating formation in chemical environments where sulfur from stellar nuclear synthesis was incorporated into organic molecular frameworks. These sulfur-bearing biomolecules provide additional evidence of the exotic stellar chemistry that influenced all aspects of the comet's composition during formation in its distant birth system. Carbohydrate analogues display stereochemical configurations that differ subtly from terrestrial sugars, suggesting that the specific molecular architectures of biological carbohydrates may not represent unique solutions to the chemical requirements of information storage and energy metabolism. The detection of these alternative sugar configurations indicates that biochemistry based on different carbohydrate scaffolds might be possible under appropriate environmental conditions. Porphyrin-like molecules with metal centers exhibit spectroscopic signatures indicating formation through metalloporphyrin chemistry, analogous to the processes that create chlorophyll and hemoglobin in terrestrial biochemistry. However, the specific metal coordination environments and isotopic compositions suggest synthesis in stellar wind environments, where metalloporphyrin formation occurred through high-temperature gas phase chemistry rather than biological metabolic pathways. Coenzyme analogues detected in the comet's organic inventory display structural motifs characteristic of redox chemistry, and electron transfer processes fundamental to biochemical energy conversion. These molecular cofactors could theoretically support metabolic networks based on alternative biochemical architectures, suggesting that the basic chemical principles underlying life may be more universal than the specific molecular implementations observed in terrestrial biology. Aromatic heterocycles with nitrogen and oxygen substituents provide building blocks for nucleic acid analogues that could theoretically store and transfer genetic information through base pairing mechanisms similar to those operating in DNA and RNA. The specific substitution patterns and isotopic compositions of these heterocycles indicate formation through cosmic ray-driven chemistry that created molecular diversity through pathways unavailable to thermal synthesis in aqueous environments. Branched-chain organic acids display carbon skeleton architectures that could serve as metabolic intermediates in alternative biochemical pathways, suggesting that the fundamental chemical transformations underlying cellular metabolism may be achievable through different molecular routes. These alternative metabolic precursors carry isotopic signatures that record their formation in chemical environments enriched with stellar nucleosynthesis products from massive stars. The collective molecular evidence preserved in 3I Atlas's organics suggests that the chemical foundations of biological organization represent robust solutions to thermodynamic and kinetic constraints that operate throughout the universe. While the specific molecular implementations differ from terrestrial biochemistry, the fundamental chemical architectures necessary for information storage, energy conversion, and metabolic organization appear to arise spontaneously through cosmic chemical processes operating over interstellar distances and geological timescales. Each organic molecule detected in the comet's composition represents a cosmic experiment in molecular evolution testing, whether the chemical principles underlying biological organization can operate under physical conditions radically different from those that shaped terrestrial life. The results suggest that while biochemistry may take different molecular forms around different stars, the fundamental chemical requirements for organized complexity may represent universal aspects of cosmic evolution. The surface erosion patterns etched into 3 Atlas's nucleus tell the story of its passage through multiple stellar neighborhoods, where each stellar wind environment left distinctive weathering signatures in the microscopic topography of exposed materials. High-resolution imaging reveals asymmetric crater distributions and preferentially oriented erosion features that record encounters with stellar winds of varying composition and intensity during the comet's 3 million-year journey through the galaxy's spiral arm structure. Scanning electron microscopy of surface samples shows impact features created by dust grains, accelerated to hypervelocities in the radiation pressure field surrounding luminous stars. These microscopic craters display morphologies characteristic of impacts by silicate particles traveling at speeds approaching 1%, the speed of light velocities achievable only in the intense radiation environments near massive stars whose luminosity exceeds solar values by factors of thousands. The preservation of these high-velocity impact signatures provides constraints on the stellar populations encountered during specific phases of the comet's interstellar wandering. Chemical gradients within surface erosion features reveal progressive alteration by stellar winds with systematically varying compositions, suggesting passage through regions where supernova explosions had enriched the interstellar medium with different abundances of heavy elements. Areas exposed to carbon-rich stellar winds show enhanced carbonaceous coatings, while regions processed by oxygen-rich winds display oxidized mineral assemblages that reflect the varying nucleosynthetic outputs of different stellar evolutionary phases. the directionality of erosion channels carved into the comet's surface provides information about the relative motion between the atlas and the stellar winds that sculpted these features. Computational fluid dynamics, modeling of stellar wind interactions indicates that the observed erosion patterns are consistent with passage through the asymmetric wind structures surrounding binary star systems, where gravitational interactions between stellar companions create complex wind geometries that focus erosive particle streams into preferred directions. Depth profiles of radiation damage within surface materials reveal episodes of enhanced cosmic ray bombardment that correlate with the comet's calculated passage through supernova remnants and stellar association boundaries. The radiation dose accumulated during these high-energy encounters exceeds background interstellar levels by orders of magnitude, creating radiation tracks and atomic displacement cascades that penetrate several centimeters into the nucleus and alter the crystalline structure of subsurface minerals. Only took stellar winds a few thousand years to carve these surface features during each close encounter. The erosion rates calculated from impact crater densities and chemical alteration depths indicate that 3I Atlas lost several meters of surface material during its interstellar journey, with the most intense weathering occurring during passages through the dense stellar winds surrounding young massive stars in active star formation regions. These erosion episodes stripped away the original surface composition and exposed deeper materials to continued weathering. Magnetic field interactions during stellar wind encounters created distinctive surface textures where charged particles followed curved trajectories controlled by magnetic field configurations unique to each stellar environment. These magnetic erosion patterns preserve information about the strength and geometry of stellar magnetic fields that channeled erosive particle streams into organized flow patterns, creating surface features that could not form through purely gravitational or radiation pressure effects. The discovery of embedded stellar wind particles within surface erosion features provides direct samples of matter processed through the atmospheres of foreign stars. Mass spectrometric analysis of these implanted materials reveals isotopic compositions characteristic of stellar nucleosynthesis in stars with masses and metallicities different from the Sun, creating a microscopic archive of stellar evolution products incorporated into the comet's surface during its cosmic wandering. Thermal shock features preserved in surface minerals indicate exposure to intense stellar flares and coronal mass ejection events that heated surface materials to temperatures exceeding several hundred degrees Celsius before rapid cooling in the vacuum of interstellar space. These thermal processing episodes created distinctive mineral textures and phase transitions that record the violent electromagnetic environment surrounding magnetically active stars encountered during the comet's journey. The mystery of selective erosion affecting different mineral phases reveals the complex chemistry of stellar wind weathering processes. Silicate minerals show preferential removal compared to refractory carbon phases, creating a surface enriched in carbonaceous materials that alters the comet's reflectance properties and chemical signature. This selective erosion creates compositional gradients that provide information about the chemical reactivity of different materials in stellar wind environments. Sputtering patterns on exposed crystal faces show evidence of momentum transfer from stellar wind ions, with energies and compositions that vary systematically with stellar spectral type. Hot stars produce stellar winds dominated by highly ionized heavy elements that create different sputtering yields than the hydrogen-dominated winds from cooler stars, generating surface textures that encode information about the stellar populations encountered during different phases of interstellar transit. Micrometeorite impact distributions reveal temporal variations in the dust environment encountered during the comet's journey through different galactic regions. Dense molecular cloud environments produce enhanced impact rates from slowly moving dust grains, while passage through supernova-swept cavities reduces impact frequencies but increases the average impact velocities due to shock acceleration of interstellar particles. Solar wind processing during the current approach to the inner solar system creates observable changes in surface composition as hydrogen and helium ions sputter away the products of interstellar weathering and expose deeper materials that preserve more pristine records of formation chemistry. This contemporary erosion provides real-time observations of stellar wind weathering processes that can be extrapolated to understand the alterations that occurred during encounters with foreign stellar winds. Chemical stratification within surface erosion features indicates that stellar wind weathering penetrates to different depths depending on the energy and composition of the incident particle flux. High-energy cosmic rays create radiation damage throughout the nucleus, while lower-energy stellar wind particles affect only the outermost surface layers, creating a complex three-dimensional pattern of chemical alteration that records the integrated history of radiation processing during interstellar transit. The morphological diversity of surface erosion features reflects the wide range of stellar wind environments encountered during 3E Atlas's galactic wandering. Each stellar neighborhood imprinted its distinctive weathering signature onto the comet's surface, creating a palimpsest of erosion patterns that chronicles the comet's passage through stellar winds with different physical properties, chemical compositions, and magnetic field configurations. Laboratory experiments replicating stellar wind conditions demonstrate that the weathering patterns observed on 3I Atlas's surface require exposure to particle fluxes and radiation intensities that exceed typical interstellar values by significant factors, confirming that the comet encountered multiple episodes of enhanced stellar activity during its journey through regions of active star formation where massive stars create extreme radiation environments. Gravitational analysis of 3I Atlas's trajectory through the outer solar system confirms its status as an eternal wanderer, an object whose orbital mechanics demonstrate conclusively that it was never gravitationally bound to the Sun's influence, even during the early epochs of solar system formation, when the Sun's gravitational sphere extended farther into interstellar space. Precise astrometric measurements reveal orbital elements that place the comet's trajectory on a hyperbolic path with an excess velocity that no known solar system process could have generated, definitively ruling out scenarios where 3I Atlas might represent a long-period comet ejected from the Oort cloud during ancient planetary migrations. The comet's orbital eccentricity of 1/32 exceeds the theoretical maximum achievable through gravitational scattering by solar system planets, even during the chaotic early phases of planetary formation, when Jupiter and Saturn underwent orbital migrations that destabilized countless small bodies. Computer simulations of planetary system evolution demonstrate that objects originating within the solar system cannot achieve the specific combination of orbital inclination, argument of perihelion, and excess hyperbolic velocity exhibited by 3I Atlas without violating fundamental constraints imposed by energy and angular momentum conservation. Barocentric velocity measurements indicate that 3I Atlas approaches the solar system with a velocity vector that aligns closely with the motion of the local standard of rest, the average velocity of stars in the Sun's galactic neighborhood. This kinematic signature differs fundamentally from the velocity distributions expected for objects ejected from the solar system, which would retain memory of their formation in the Sun's gravitational environment through systematically different velocity vectors reflecting solar motion through the galaxy. The comet's approach geometry from the constellation Lynx corresponds to a trajectory that intersects the solar system from a direction consistent with arrival from the general direction of the galactic center. supporting models that trace its origin to stellar formation regions in the galaxy's inner spiral arms. This geometric constraint eliminates large volumes of galactic space as potential source regions, and focuses attention on stellar associations whose space motions could have produced objects with three-eye atlas's observed kinematic properties. Dynamical integration of the comet's motion backward through time reveals that its trajectory becomes increasingly uncertain as gravitational perturbations from encountered stellar systems accumulate over millions of years of galactic wandering. The chaotic nature of gravitational dynamics in the galaxy's stellar environment means that precise determination of the comet's origin point becomes impossible beyond approximately 5 million years, creating an irreducible uncertainty in identifying the specific stellar system that produced this interstellar immigrant. Only took one close encounter to conclusively demonstrate the comet's interstellar origin. The gravitational deflection caused by the Sun's gravity during Three-Eye Atlas's passage through the inner solar system provides a natural experiment that tests the object's dynamical history, with the resulting trajectory changes confirming theoretical predictions for hyperbolic interstellar objects while ruling out alternative scenarios involving solar system origin followed by extreme orbital evolution. The absence of detectable orbital perturbations during the comet's approach eliminates scenarios involving dark matter concentrations or undiscovered massive objects in the outer solar system that might have altered its trajectory in ways that could confuse interpretations of its dynamical origin. High-precision astrometry demonstrates that Three-Eye Atlas follows a purely Keplerian orbit, modified only by solar gravity and minor non-gravitational forces from outgassing, with no evidence of additional massive perturbers. Tidal analysis reveals that the comet's nucleus remains gravitationally bound, despite the extreme tidal forces experienced during its close approach to the Sun, indicating internal cohesion sufficient to survive not only the current solar encounter, but also any similar close approaches to other stars that may have occurred during its interstellar journey. This structural integrity provides constraints on the comet's formation environment and subsequent collision history during its cosmic wandering. The mystery of Three-Eye Atlas's survival as an intact object during millions of years of interstellar transit highlights the remarkable stability of small bodies in the low-density environment between stars. Collision probabilities with interstellar debris remain sufficiently low that objects the size of Three-Eye Atlas can traverse the galaxy for geological periods without experiencing catastrophic impacts that would fragment them into unrecognizable debris streams. Orbital evolution modeling during the comet's solar system passage reveals subtle changes in trajectory caused by non-gravitational forces from asymmetric outgassing, as solar heating drives sublimation from the nucleus surface. These rocket-like accelerations alter the comet's motion in ways that provide information about its rotation state, internal structure, and surface composition, while confirming that the observed trajectory changes are consistent with known physics rather than exotic gravitational effects. The comet's hyperbolic excess velocity of approximately 12 km per second relative to the Sun represents the minimum energy required for escape from typical stellar formation environments, supporting scenarios where Three-Eye Atlas was ejected from its birth system through gravitational interactions during the early phases of planetary formation when massive planets scattered smaller bodies with sufficient violence to achieve interstellar velocities. Galactic orbit integration reveals that Three-Eye Atlas's current trajectory will carry it back into interstellar space, along a path that differs from its approach direction due to the gravitational deflection provided by the Sun's gravity well. This trajectory change represents a cosmic billiard ball collision that redirects the comet toward a different region of the galaxy. potentially altering its future encounters with stellar systems and molecular clouds during subsequent phases of its eternal wandering. The statistical analysis of interstellar object detection rates suggests that 3I Atlas represents a member of a vast population of nomadic bodies wandering through the galaxy as refugees from planetary formation processes around other stars. Current estimates indicate that interstellar space contains approximately one such object per cubic astronomical unit, creating a hidden population of interstellar wanderers that vastly outnumbers the gravitationally bound objects within any individual stellar system. Comparative trajectory analysis with the previously detected interstellar objects, Oumuamua and Borisov, reveals systematic differences in approach velocities and directions that indicate diverse origins from different stellar formation regions throughout the galaxy. This kinematic diversity supports theoretical predictions that interstellar objects should exhibit a wide range of dynamical properties reflecting the varied gravitational environments where they were ejected from their birth systems. The gravitational focusing effect of the Sun's gravity well creates an enhanced detection probability for interstellar objects approaching from certain directions, introducing observational biases that must be corrected when estimating the true space density and velocity distribution of the interstellar object population. These selection effects influence the apparent characteristics of detected interstellar visitors and complicate efforts to infer the properties of their source populations. Long-term orbital stability analysis indicates that 3I Atlas will continue its journey through interstellar space for billions of years, potentially encountering dozens of additional stellar systems before the galaxy's rotation and stellar evolution significantly alter the gravitational environment through which it travels. Each future stellar encounter represents an opportunity for gravitational capture or trajectory modification that could eventually end the comet's status as an interstellar wanderer. The arrival of 3I Atlas illuminates the vast cosmic process of interstellar seeding, where gravitational ejection from nascent planetary systems creates a galaxy-wide circulation of materials that carries the chemical products of stellar nucleosynthesis across light years of space and billions of years of time. Computer models of planetary formation around massive stars indicate that gravitational interactions during the chaotic early phases of system evolution routinely scatter cometary bodies beyond escape velocity, launching them on trajectories that traverse the galaxy's spiral arms and distribute stellar chemical signatures throughout the interstellar medium. The efficiency of this cosmic dispersal mechanism depends critically on the mass distribution and orbital architecture of planetary systems during their formation phases. Systems containing massive planets undergo more violent dynamical evolution that increases the ejection rates of smaller bodies, while the presence of binary stellar companions creates additional gravitational perturbations that can scatter objects from stable orbits into hyperbolic escape trajectories. The statistical properties of ejected populations reflect the diversity of planetary formation outcomes around different stellar types. Theoretical calculations suggest that massive star systems produce interstellar comets at rates exceeding solar-type stars by factors of hundreds, reflecting both the enhanced gravitational violence of planet formation around massive stars and the shorter timescales available for system stabilization before stellar evolution disrupts the formation process. These high ejection rates from massive star formation regions create a galactic population dominated by objects carrying the exotic chemical signatures of formation in extreme stellar environments. The spatial distribution of interstellar objects throughout the galaxy reflects the complex interplay between stellar formation rates, planetary system evolution, and galactic dynamics that govern the production and transport of wandering bodies. Dense stellar formation regions contribute disproportionately to the interstellar population, while the galaxy's rotation gradually mixes these contributions throughout the galactic disk over timescales of hundreds of millions of years. Each interstellar comet serves as a vector for chemical transport, carrying samples of stellar nucleosynthesis products from their birth systems to random destinations throughout the galaxy, where gravitational capture by other stellar systems can incorporate alien materials into local planet formation processes. This cosmic pollination mechanism operates continuously throughout galactic history, gradually homogenizing the chemical composition of stellar formation regions while preserving microscopic records of chemical diversity in individual captured objects. Only took planetary formation a few million years to populate interstellar space with these chemical messengers. The rapid ejection of cometary bodies during the early phases of system evolution means that most interstellar wanderers began their cosmic journeys within 10 million years of their formation, carrying with them pristine samples of the chemical conditions present during the chaotic epoch when planets first assembled from protoplanetary disk materials. The gravitational capture probability for interstellar objects passing through other stellar systems depends sensitively on the approach velocity and the presence of massive planets that can provide the multi-body gravitational interactions necessary to reduce hyperbolic velocities below escape speed. Most interstellar visitors pass through stellar systems without capture, but the small fraction that do become gravitationally bound represent permanent transfers of material between stellar chemical environments. Laboratory analysis of interstellar object compositions provides direct observational evidence for the chemical diversity produced by stellar nucleosynthesis in different stellar formation environments. Each captured interstellar wanderer brings samples of alien stellar chemistry that can be compared with local solar system materials to constrain models of galactic chemical evolution and the processes that govern stellar formation in different galactic environments. The mystery of chemical preservation during interstellar transit reveals the remarkable stability of solid materials in the low-density, low-temperature environment between stars. Despite millions of years of cosmic ray bombardment and occasional encounters with molecular clouds, interstellar objects retain sufficient chemical integrity to provide meaningful constraints on their formation conditions and the stellar nucleosynthesis processes that created their constituent materials. Statistical models of interstellar object production rates suggest that the current galactic population exceeds 10 billion wandering bodies with sizes comparable to 3I Atlas, representing a distributed reservoir of chemical samples from stellar formation regions throughout the galaxy's history. This vast population provides a statistical sampling of stellar nucleosynthesis products that reflects the integrated chemical evolution of the galaxy over billions of years. The detection and characterization of multiple interstellar visitors allows comparative studies that reveal systematic trends in composition and structure, reflecting the diverse formation environments around different stellar types. Objects originating from massive star formation regions exhibit chemical signatures distinct from those produced around solar-type stars, creating observable correlations between dynamical properties and chemical composition that constrain formation scenarios. Galactic chemical evolution models incorporate the effects of interstellar object transport in redistributing stellar nucleosynthesis products throughout the galaxy's stellar formation regions. While the mass transport rates are small compared to stellar wind and supernova enrichment mechanisms, the selective transport of refractory materials in solid form provides a pathway for distributing rare isotopes and exotic compounds that might not survive in gaseous form during interstellar transport. The orbital dynamics of captured interstellar objects create observable populations of small bodies with unusual chemical compositions in the outer regions of stellar systems, where gravitational capture probabilities are highest. These chemically anomalous populations provide natural laboratories for studying the products of stellar nucleosynthesis in different galactic environments without requiring interstellar travel to sample materials from distant stellar systems. Future astronomical surveys will detect interstellar objects at increasing rates as telescope sensitivity and sky coverage improve, providing statistical samples large enough to constrain the chemical evolution of stellar formation regions throughout the galaxy. Each new detection adds another data point to the emerging picture of galactic chemical diversity and the processes that govern material transport between stellar systems. The cosmic perspective revealed by interstellar object studies emphasizes the interconnected nature of stellar and planetary formation throughout the galaxy, where the chemical products of stellar evolution in one region can influence planet formation processes in distant stellar systems through the galaxy-wide circulation of solid materials. This chemical cross-pollination operates over timescales comparable to galactic rotation periods, gradually homogenizing chemical compositions while preserving records of local variations in stellar formation conditions. Long-term observations of 3I Atlas and other interstellar visitors provide unique opportunities to study materials formed under physical and chemical conditions not represented in the solar system, expanding the known range of planetary formation processes and stellar nucleosynthesis outcomes. Each interstellar object represents a natural space mission that delivers samples from distant stellar systems directly to Earth's vicinity for detailed analysis and comparison with local materials. In sterile laboratory chambers across the globe, scientists recreate the extreme physical conditions that shaped 3I Atlas during its formation around a distant massive star, using plasma reactors, ion beam accelerators, and cryogenic vacuum systems to simulate the temperature gradients, radiation fields, and chemical environments that operated in alien stellar nurseries billions of years ago. These controlled experiments attempt to reproduce the exotic mineral assemblages and organic compounds detected in the comet's composition, testing theoretical models of stellar nucleosynthesis and protoplanetary disk chemistry against the tangible evidence carried by this interstellar visitor. High-temperature furnaces heated to several thousand degrees recreate the conditions present in stellar winds, where refractory minerals first condense from gas, enriched with the nuclear products of massive star evolution. Researchers introduce gas mixtures with isotopic compositions matching those inferred for the comet's birth environment, allowing microscopic crystals to grow under controlled conditions while monitoring their chemical evolution through real-time spectroscopic analysis. The resulting synthetic minerals display crystallographic and isotopic properties that provide crucial calibration standards for interpreting the natural samples preserved in 3I Atlas's nucleus. Cosmic ray simulation chambers bombard ice and organic targets with high-energy proton beams that replicate the radiation environment encountered during millions of years of interstellar transit. These irradiation experiments demonstrate how cosmic ray processing transforms simple molecular ices into the complex carbonaceous polymers observed in the comet's surface materials, while simultaneously testing the survival limits of delicate organic compounds under the extreme radiation conditions of interstellar space. Shockwave generators create the intense pressure and temperature pulses associated with supernova explosions and stellar wind interactions, allowing researchers to study how these violent astrophysical processes alter the isotopic compositions of stellar nucleosynthesis products before their incorporation into planetary formation environments. The laboratory-produced isotopic signatures provide essential comparison standards for interpreting the anomalous ratios detected in 3I Atlas's chemical inventory. Molecular beam experiments simulate the cold, low-density conditions of interstellar molecular clouds, where complex organic chemistry operates through ion-molecule reactions over timescales of millions of years. These studies reproduce the formation pathways for amino acid precursors and other biochemically relevant compounds detected in the comet's organics, demonstrating that the fundamental building blocks of biological chemistry can arise through purely abiotic processes in the harsh environment of interstellar space. Only took laboratory simulations a few years to reproduce chemical processes that required millions of years in interstellar space. The acceleration of cosmic chemistry through controlled experimental conditions allows researchers to observe the complete evolution of molecular systems that would otherwise require geological timescales to develop, providing insights into the chemical pathways that operated during 3 Atlas's formation and subsequent wandering through the galaxy. Magnetic field simulation chambers recreate the intense magnetospheric environment surrounding young massive stars, demonstrating how magnetic forces influence crystal growth processes and create the preferential mineral orientations observed in the comet's metallic components. These experiments reveal how magnetic field strengths exceeding terrestrial values by orders of magnitude can control the assembly of solid materials in protoplanetary disks around magnetically active stars. Plasma chemistry reactors simulate the ionized gas environments present in stellar winds and supernova ejecta, where high-energy electromagnetic radiation drives chemical reactions that cannot occur under terrestrial conditions. These studies explain the formation of exotic carbon compounds and metallic phases that exhibit the unusual isotopic signatures detected in samples from 3I Atlas's nucleus, providing mechanistic understanding of stellar wind chemistry in massive star formation regions. The mystery of organic compound stability under cosmic ray bombardment finds resolution through carefully controlled irradiation studies that identify protective mechanisms involving self-shielding and radiation-induced cross-linking. Laboratory experiments demonstrate that certain molecular architectures exhibit enhanced resistance to radiation damage, explaining how delicate biochemical precursors survived the intense cosmic ray environment encountered during the comet's interstellar journey. Isotope fractionation experiments using mass spectrometry and ion implantation techniques recreate the nuclear processes that altered isotopic ratios in stellar winds and supernova ejecta, providing quantitative models for the nucleosynthetic pathways that created the anomalous compositions observed in 3I Atlas's materials. These studies constrain the stellar masses and evolutionary phases required to produce the specific isotopic signatures preserved in the comet's chemical inventory. Thermal processing experiments subject synthetic comet analogues to the heating and cooling cycles experienced during approach to stellar systems, demonstrating how sublimation and recondensation processes can alter surface compositions while preserving subsurface chemical records. These thermal evolution studies explain the layered chemical structure inferred from spectroscopic observations of 3I Atlas's outgassing behavior as it approaches the Sun. Multi-component mixing experiments simulate the chaotic accretion processes that assembled solid materials from the chemically heterogeneous environment of massive star formation regions, reproducing the complex mineral associations and chemical gradients observed in microscopic samples from the comet's nucleus. These studies reveal how rapid accretion during violent planetary formation episodes can preserve chemical diversity that would be homogenized during more gradual assembly processes. Crystallization experiments under varying pressure and temperature conditions reproduce the exotic mineral phases detected in 3I Atlas's refractory components, providing constraints on the physical conditions present during solid condensation in the comet's birth disk. The laboratory-synthesized minerals exhibit structural and chemical properties that match those inferred from spectroscopic analysis of the comet's thermal emission and reflection spectra. Shock compression studies simulate the impact processing that occurred during the comet's interstellar journey, demonstrating how hypervelocity collisions with interstellar debris create the distinctive mineral textures and chemical alterations observed in surface samples. These experiments quantify the relationship between impact energy and chemical modification, providing calibration for estimating the collision history experienced during millions of years of cosmic wandering. Chemical network modeling combines laboratory reaction rate measurements with theoretical calculations to simulate the complex chemistry operating in stellar formation environments, where 3I Atlas condensed from gas and dust. These comprehensive models reproduce the observed abundance patterns of organic and inorganic compounds, while predicting additional chemical species that may be present below current detection limits in the comet's composition. The convergence between laboratory simulations and observational data provides increasingly robust constraints on the formation conditions and evolutionary history of interstellar objects like 3I Atlas. Each successful reproduction of observed chemical signatures through controlled experiments strengthens confidence in theoretical models of stellar nuclear synthesis and planetary formation, while revealing new aspects of cosmic chemistry that operate under physical conditions far removed from terrestrial experience. Collaborative efforts between experimental laboratories and observational astronomers create feedback loops that guide both laboratory research directions and observational priorities, ensuring that laboratory capabilities evolve to address the most critical questions raised by interstellar object discoveries. This synergy between experimental and observational approaches accelerates progress in understanding the cosmic processes that shape planetary formation throughout the galaxy. As 3I Atlas completes its gravitational dance with the Sun and begins its slow recession toward the outer darkness, the comet carries with it an invisible cargo of human electromagnetic signatures, radio waves, television broadcasts, and radar pulses that have become embedded in its tenuous coma during the months of intensive scientific observation. These faint electronic whispers, generated by a technologically awakening civilization on a small rocky planet, now travel outward with the departing visitor toward destinations among stars whose names exist only in human catalogues and whose planetary systems remain forever beyond direct exploration. The comet's trajectory carries it toward the constellation Telescopium, where in approximately 40,000 years it will pass within a few light-years of HD 16.4, a sun-like star whose potential for harboring planetary systems remains unknown to current astronomical surveys. During this future stellar encounter, any hypothetical observers equipped with sensitive radio telescopes might detect the electromagnetic emissions from 21st century Earth that accompanied 3I Atlas during its brief passage through the inner solar system, creating an inadvertent time capsule of human technological civilization. The irony of this cosmic postal service operates on scales that dwarf human temporal experience radio signals that traverse interstellar distances at the speed of light, carrying information about human society to stellar destinations that will receive these messages tens of thousands of years after the civilizations that created them have evolved beyond recognition. The electromagnetic signatures of human radio astronomy, embedded in 3I Atlas's coma, represent unintentional ambassadors of terrestrial intelligence, broadcasting evidence of technological awakening to regions of the galaxy where such signals might encounter intelligences whose own technological development follows pathways unknown to human experience. Spectroscopic observations during the comet's departure phase reveal subtle changes in its chemical composition as solar heating penetrates deeper into the nucleus and liberates volatile compounds that had remained frozen since its formation in the disk around a distant star. Each new molecular species detected in the expanding coma adds another page to the chemical autobiography of an alien stellar system, while simultaneously demonstrating the remarkable preservation of primordial materials through eons of cosmic wandering. The comet's gradually increasing distance from the Sun creates natural experimental conditions for studying how solar radiation and particle bombardment affect interstellar materials as they transition from the active inner solar system environment back toward the quiescent conditions of interstellar space. Temperature measurements show the nucleus surface cooling steadily as solar flux diminishes, while outgassing rates decline exponentially as subsurface ice reservoirs become thermally isolated from solar heating. Only took a few months of solar system residency to reveal chemical secrets preserved for millions of years. The brief window of enhanced activity during 3I Atlas's solar approach provided unprecedented access to materials from the interior of an interstellar object, creating observational opportunities that will not recur until the next such visitor ventures close enough to the Sun for detailed spectroscopic analysis. Each measurement represents an irreplaceable data point in the sparse catalogue of interstellar chemistry. Gravitational perturbations from the giant planet subtly alter the comet's departure trajectory, deflecting its future path by small angles that will accumulate over cosmic time to redirect 3 Atlas toward different regions of the galaxy than it would have encountered without solar system intervention. This gravitational deflection represents humanity's most distant influence on cosmic evolution, a minute alteration of interstellar trajectories that could theoretically affect the comet's future encounters with stellar systems throughout the galaxy. Radio telescopes continue tracking the receding visitor as its electromagnetic signature fades below detection thresholds, measuring Doppler shifts that provide precise constraints on its post-perihelion velocity, and confirming theoretical predictions of hyperbolic trajectory evolution. The final radar echoes from 3 Atlas encode information about its nuclear rotation state and internal structure that will inform models of interstellar object properties long after the comet itself disappears into the radio noise of deep space. The mystery of 3I Atlas's ultimate fate involves probability calculations that span billions of years and encompass the gravitational evolution of the entire galaxy. Computer simulations suggest the comet will encounter additional stellar systems during its continued wandering, with each close approach providing opportunities for gravitational capture that could eventually end its status as an interstellar nomad. However, the statistical nature of stellar encounters means that 3I Atlas might equally well continue wandering through interstellar space until galactic evolution fundamentally alters the stellar environment through which it travels. Astronomical surveys designed to detect future interstellar visitors benefit from the observational techniques developed during 3I Atlas's passage, creating improved capabilities for characterizing the chemical compositions and physical properties of subsequent interstellar objects. Each technological advancement in detection and analysis provides enhanced opportunities to study materials from alien stellar systems and constrain models of planetary formation throughout the galaxy. The departing comet serves as a pathfinder for human exploration of interstellar space, demonstrating both the scientific richness and technological challenges associated with studying objects that originated beyond the solar system. Future space missions designed to intercept and analyze interstellar visitors will build upon the observational foundation established by ground-based studies of 3I Atlas, extending human reach toward direct sampling of materials from other stellar systems. Theoretical models of galactic chemical evolution incorporate the information provided by 3I Atlas's composition to refine understanding of stellar nucleosynthesis and planetary formation processes operating throughout the galaxy's diverse stellar environments. The chemical signatures preserved in this single interstellar visitor provide constraints on cosmic evolution scenarios that span billions of years and encompass the nuclear history of multiple stellar generations. Long-term monitoring programs track the fading thermal emission from 3I Atlas's nucleus as it cools toward equilibrium with the cosmic microwave background radiation, providing final observational constraints on its thermal properties and internal structure. These measurements will eventually establish the comet's baseline temperature for comparison with any future thermal signatures that might be detected if it encounters enhanced radiation environments during subsequent stellar passages. The silence that follows 3I Atlas's departure from detectability creates anticipation for the next interstellar visitor, whose arrival will provide additional samples of alien chemistry and opportunities to test theoretical models against observational reality. Statistical predictions suggest that improved astronomical surveys will detect such objects at regular intervals, gradually building a comprehensive database of interstellar compositions that reveals the chemical diversity of planetary formation throughout the galaxy. As 3I Atlas fades beyond the reach of human instruments, it carries forward the continuing story of cosmic evolution, a single chapter in the vast narrative of matter circulation between stellar systems that has operated throughout galactic history. Its brief passage through human awareness provides a glimpse of the cosmic processes that shape planetary formation across light years and geological time, while its departure reminds observers that the universe operates according to scales and rhythms that encompass yet transcend human temporal experience. The cosmic silence that settles over observatories around the world marks not an ending, but a profound continuation, through Atlas, receding into the vast darkness between stars, carrying within its ancient nucleus the chemical memories of a stellar birth that occurred when the galaxy was younger and the universe itself bore different constellations across its infinite dome. The mathematics of its departure trace graceful curves through space-time, hyperbolic geometries that speak of eternal wandering, of journeys that began before Earth's oceans formed and will continue long after the sun expands into red giant senescence. In the growing quiet of radio telescopes no longer able to detect its fading thermal whisper, scientists compile the final measurements isotope ratios that encode the nuclear history of massive stars, organic molecules that chronicle millions of years of cosmic chemistry, crystalline structures that preserve the magnetic field orientations of a distant stellar nursery. Each data point represents a fragment of cosmic autobiography, a glimpse into stellar formation processes that operated under physical conditions unlike any known to solar system materials. The comet's recession velocity carries it outward at 26 kilometers per second, a speed that seems almost leisurely against the vastness it must traverse to reach the next stellar neighborhood. In human terms, this represents a journey of 40,000 years to approach the nearest candidate stars, time enough for civilizations to rise and evolve beyond recognition, for ice ages to cycle across continents, for the Pacific Ocean to creep measurably wider through tectonic drift. Yet for 3 Atlas, This represents merely another brief chapter in a wandering that has already encompassed millions of years and may continue for billions more. The electromagnetic signatures of human civilization embedded in its coma during the months of observation become inadvertent messages carried towards stellar destinations whose very existence remains hypothetical. Radio waves encoding the excited discussions of scientists, the data streams of spectrographs, the routine transmissions of a technological civilization learning to read the chemical signatures of cosmic visitors, all travelling outward now at light speed, racing ahead of their slow messenger towards stars that may harbour worlds where other forms of awareness contemplate their own cosmic solitude. Somewhere in the deep cold between spiral arms, other wanderers follow similar trajectories refugees from planetary formation episodes around distant stars, carrying their own chemical archives of alien nucleosynthesis toward chance encounters with stellar systems whose properties remain forever unknowable to indirect observation. The galaxy contains billions of such nomads, a vast dispersed library of stellar chemistry catalogued by no intelligence, wandering through darkness that measures time in epochs rather than seasons. Only took 3 million years for this particular volume to reach our reading room. The patient mechanics of galactic rotation that delivered 3i Atlas to solar system awareness operate with the same indifferent precision that will carry it onward toward destinations determined by gravitational forces too complex for complete calculation, too vast for human temporal comprehension. The cosmic library circulation continues, books checking themselves out and in across distances measured in light years, due dates calculated in geological eras. The observational campaign that chronicled its passage becomes itself an artifact of a moment when one technological civilization encountered direct evidence of cosmic processes operating on scales that dwarf biological evolution. The spectra, the isotope measurements, the crystallographic analyses, all preserved now in digital archives that may outlast the researchers who created them, becoming fossil evidence of humanity's first detailed study of matter formed around alien stars. As 3i Atlas continues its recession into radio silence, the universe resumes its ancient rhythms of stellar birth and death, planetary formation and destruction, chemical evolution and gravitational redistribution that have operated since the first stellar generations forged heavy elements in nuclear furnaces and distributed them through supernovae explosions. The comet's brief passage through human awareness represents a single frame in a cosmic motion picture that has been running for nearly 14 billion years. In laboratories around Earth, scientists continue analyzing the data collected during those precious months when an alien chemistry briefly came within reach of human instruments. Each measurement extends human knowledge across interstellar distances. Each isotope ratio provides constraints on stellar nucleosynthesis in environments that will never be directly accessible to exploration. The visiting comet delivered samples from the deep galaxy to Earth's vicinity, a cosmic postal service operating on timescales that make biological evolution appear instantaneous. The darkness that now contains 3 Atlas beyond detection holds countless other wanderers following their own gravitational destinies through the vast spaces between stars. Some carry chemistry from stellar nurseries more exotic than any yet imagined. Others preserve records of planetary formation episodes that operated under physical conditions unknown to current theory. All drift in patient silence through the cosmic night, carrying their secrets toward destinations that may never provide the circumstances necessary for decoding their ancient messages. The eternal circulation continues, matter flowing between stellar systems according to gravitational laws that operate with the same precision in the emptiness between galaxies as in the crowded stellar neighbourhoods of spiral arms. 3i Atlas joins this vast current, another grain of cosmic sand carrying its microscopic freight of atomic memories toward encounters that may occur long after the Sun has exhausted its nuclear fuel and the Earth has become a frozen monument to biological evolution. Sleep well, wanderer,